Okay, welcome back, everybody. I'll give the same reminders, which is feel free to use the chat if you want to engage, and if you want to not show up on the recordings, um, just be cautious about how you unmute and turn on your video and stuff. All right. Last class, we talked about MO theory and how it is the justification for why alkenes react the way they do. MO theory was also our justification for why pi bonds are stereocenters. Why pi bonds, and I should say alkenes, but it is true, pi bonds. Why alkenes are stereocenters and are not able to rotate around their bonds. Let me take you back to when we talked about Newman projections. And we saw how we could take um, sigma bonds, rotate around them, and produce new conformations where uh, absolute configuration and absolute stereochemistry is preserved because no bonds are breaking or forming. But the way that it takes up space and the perception that we get of it changes. Notice how my bond line goes from zig-zig to zigzag. No, I said that backwards. Notice how it goes from zigzag to zig-zig. Well, that is not allowed with alkenes. If I have a quote unquote zigzag alkene, we learned that we can use terminology like trans or the abbreviation for the German word E, or my fun little way of just calling it high priority groups are on opposite sides, point in opposite directions. We are not allowed to rotate around this to try and get this alkene into a zig-zig configuration, even though it is a perfect analog of what we did back in Unit 2 with Newman projections. And that's because the existence of the pi bond, which depends on orbital overlap with the lobes in phase. Remember that orbitals are just mathematical equations. So this is saying when the parts of the wave that go up overlap and when the parts of the wave that go down overlap. Again, like taking waves in the ocean and overlapping them constructively, that gives us our orbital. But if I take one of those carbons and I try to physically rotate it and change its orientation in space, my wave is now taking my wave sees start over, deconstructive interference, and it breaks the bonding character. So it can happen. It happens when we process natural unsaturated fats. And that's how we go from having healthy cis fats to less healthy trans fats. The conversation about why cis fats are healthy and why trans fats are less healthy is another very interesting conversation, and it really comes down to how structure impacts intermolecular forces and how intermolecular forces accumulate inside of your body. But I will leave that for your nutrition classes. I want to keep with this example, but I want to change something. Um, on the left, I've given you a chiral molecule with two chiral centers, and I'm showing you the absolute configuration at those chiral centers. We can prioritize the groups, rank them 1 to 4, recognize whether 4 is coming forward or backwards, obeying our rules, determine rotation from 1 to 2 to 3, assign RRS. Sorry, that bottom structure was a diastereomer of it. But if I were to put chlorine atoms in a similar position, On my alkene carbons, you'll notice that I will intentionally leave off wedges and dashes. I wonder if anyone wants to pop into the chat why they think I would never draw wedges and dashes for the chlorines coming off of those alkene carbons. Think about how you could boil it down to one word or one concept. And I'm not going to actually force you guys to pop it in the chat, but I want to give you that chance. Great. Comes down to its molecular geometry and our artistic representations of three-dimensional things on two-dimensional media. I have a tetrahedral carbon that is chiral, and I can show how it takes up three-dimensional space using wedges and dashes, but I represent it on a flat surface. Um, Now I have a trigonal planar carbon. It is flat. So representing it on a flat surface is really easy. There is nothing to show. I just show a line. In fact, this is something that I look for when I'm grading in this unit. If you show me something like a stereo perception, a wedge or a dash on a trigonal planar carbon, it it tells me, it helps me assess that that is where you're lacking in your understanding of the fundamental physics of the structure. And I do want to point out, it's not inherently wrong to show wedges and dashes on planar carbons, but you do have to think about the reality of it. I can take something that's flat and I can turn it on its side. If I have it flat and I'm looking at the top or the bottom, then I can keep everything flat. I don't need to show any wedges or dashes because they don't exist. If I turn it onto its side, there suddenly is things going away from me, things coming towards me. So I can show trigonal planar um, groups with wedges and dashes, but I have to be consistent. If there's a wedge coming for one group, I did that a little wrong, didn't I? If there's a wedge coming from one group, then there's a dash going to the other. There's no picking and choosing. I'm looking at it on its side. So bad representation of a trigonal planar carbon has one group wedged, one group dashed, doesn't exist. Good representation has everything flat. And a more sophisticated, a more advanced representation shows things wedged going away and, sorry, wedged coming towards you and dashed going away um, consistently, showing something on its side. And actually, this is where we can start to understand the top face and the bottom face. Again, this is artistic representation. Imagine that I'm trying to draw a flat piece of bread. I'm not good at it. But if I wanted to show you that my flat piece of bread is on its side, I have to do a little bit more work in convincing you that I recognize it's on its side. I have to give you depth. I have to show things coming towards you and things going away from you. Chemists are artists. We're just not trained for that. Okay, so stereocenters can apply to alkenes like stereocenters can apply to tetrahedral carbons, but the example of on the left of the chiral molecule has tetrahedral carbons that are chiral and ones that are not stereocenters, and that's because they lack two unique groups at both carbons. All right. Um, we're going to talk about a really beautiful aspect of stereocenters, which is The symmetric alkene, which is flat and has a top face and a bottom face, kind of like how our piece of bread analogy has a top thing has a top face and a bottom face, and these can go through chemical reactions, add new groups to those carbons, and create chiral centers. So let's take, for example, um, if I use this alkene in the middle row at the top. Now, I want you guys to be thinking about how to do nomenclature. If you guys have specific nomenclature ones that you want to look at with me, I'm happy to go through those. Otherwise, I think I may have done them all in the fall semester. So you can look back at my fall 2025 lecture recording and get the names for all of them, or point out specific ones that you want to name or draw, and I'm happy to go through those. Otherwise, I want to take some time moving faster and getting into some more material today. If I take this, whose name prioritizes the lowest locant for the alkene, gives us 3-methyl, 1-butene, and yes, I must say the location of the alkene. It cannot be assumed that it is at position 1 because there are structural isomers where the alkene can move along the carbon chain. Um, 3-methyl 1-butene can go through addition reactions. I want you to consider for a minute if I add bromine as my two groups, elemental bromine, and that means two bromines get added, one bromine to each carbon, and I add a bromine on the left and I add a bromine on the right. This is a reaction that we'll talk about, probably not later today, but definitely next week. And Kirsten, your clarification is exactly right. We could also call this 3-methyl but-1-ene because that locant can go before the root. IUPAC doesn't really like that. They like it going before what it describes, which is the suffix. Now, we went from having a flat trigonal planar group, uh, and and now I have two tetrahedral carbons. So one question that I have is, did the bromines bond to the carbons in a way that they were added to the top face? Notice how in my three-dimensional perspective, the four groups originally attached are still attached in the same way. I have a hydrogen back, a hydrogen forward, a hydrogen forward, and isopropyl back. It's not really isopropyl, but it is. And it looks like the bromines have added right to the top face. Or do the bromines add to the bottom face? Do you guys see where I'm coming from with this? How my trigonal planar alkene carbons were flat, and there's the possibility that they can have new bonds added from the top or from the bottom. Trigonal planar into sp3. Or is it possible that it's one and the other? For instance, if they both add to the same face, we call it syn addition. If they add to opposite faces, we call it anti-addition. And if there's no control, if I can get the two groups sometimes react with the alkene syn, sometimes anti, and it's a total random combination of adding to the faces, then we can call it random addition, but there's no one rule to it. We will be using terminology like this to describe our reactions with alkenes. Did the two groups add syn when becoming tetrahedral carbons? Did they add anti when becoming tetrahedral carbons? Was it random? But one question is, why does it matter? Who cares if they've added syn or anti? Do you know what? Sorry, I'm just going to point out one thing that I'm really struggling with doing this on Zoom. I show so much more than I think I would in class, and it's a lot less organized than it would be if I were on the board. So I apologize for that, and especially the lack of clarity that can come across on Zoom. Please let me know if there are any structures you'd like me to redraw or go back to, and just feel free to pop in the chat if you want to do that. Why would it matter? If I create a tetrahedral carbon from a trigonal planar carbon and the two new tetrahedrals are syn addition, anti-addition, or random, it matters when I create chiral centers. For instance, this reaction creates only one chiral center. The carbon on the right has two hydrogens, achiral, but the carbon on the left, the more substituted carbon of the alkene, now has four distinct groups. If my bromine added to the top, I'll show it as a wedge, I get one absolute configuration. If it added to the bottom, I get a different absolute configuration. So one chiral carbon leads to the production of enantiomers. Now, if we consider cyclopentene, think about if you can identify where cyclopentene is. Cyclopentene goes through a similar reaction with bromine. Two new groups add, both new groups are bromines. This time I create two chiral centers. If my bromines have added syn, then I only get one product. I get cis 1,2-dibromocyclopentane. I get 1R, 2S, 1,2-dibromocyclopentane. This is a meso compound, so it has no enantiomer. It is symmetric to its mirror image. But if my bromines add anti, then I get two possibilities. I have the possibility of 1R, 2R. Well, that was wrong. The one on the left, the one I just drew is 1S, 2S, or 1R, 2R. These are enantiomers. So do I get trans 1,2-dibromocyclopentane? Do I get cis? There's important implications that come from that. Uh, they now have different physical properties and they'll have unique chemical properties. If I'm running this in a multi-step synthesis, if I'm trying to create a drug, I need to know what the absolute configuration is because it's possible that one version of this cures the cancer I'm aiming for, the other causes cancer, and the mesodiastereomer does nothing. So I need to know what my chemical reactions are doing, how their stereochemistry results. And then we can continue adding to this. We can have a molecule that already has a stereocenter that's not changed by a chemical reaction. And then we get diastereomer products. But again, what combination of diastereomers, syn or anti-addition, results from this flat trigonal planar starting material, having things added either to the bottom or the top or both. So that's where we're heading. If you have specific molecules, I know, I'm sorry, I didn't number them. You can say like left, middle, right, and what number down. If you have specific molecules you want to talk about, I would be happy to go through them. But if you want practice problems, you've got them. While we talk about how alkenes can react, it's important for us to also talk about how alkenes can be formed. We will come back to the chemical reactions um, in Unit 5, and we'll look more at the mechanisms. You've already seen some of them. We'll look at the mechanisms. We'll look at the reagents more specifically. We'll also look at competitions. Um, Sometimes A and B, two chemicals, don't always react to form just C and D. Sometimes A and B react to form E and F plus C and D. And different possibilities can result, and you need to deal with the combinations of those different possibilities, control your conditions to be able to promote the ones that you're interested in. Okay, before we do that, I'm happy to look at the bottom right structure. 3 bromo, 1 methyl, cyclopentadiene. Oh, okay, so where is the second alkene? Have I failed you as your instructor because I don't have any locants? It is limited in the ability to have positions. So in this case, the locants for the two alkenes is unnecessary. It's kind of like when we call, sorry, it's kind of like when we call that top right structure cyclopentene, place it can be. When we call it cyclopentadiene, there is only one combination of two alkenes. No matter where I move the second alkene, it will always be in the same position. And I would love for someone to say, why are you ignoring the case where the second alkene, but I am ignoring it because, oh man, my drawings are not clearing. I'm ignoring the possibility where the two alkenes share a carbon, which is called a uh, cumulated diene, meaning they meet at the same point, they come together at the same point. I'm ignoring that because in the ring, I'm aiming for 109 degrees, or somewhere between 109 and 120 degrees for a bond angle. But an sp hybridized carbon would want an 180 degrees, so it's not one of our feasible expectations for it. So I can place my two alkenes wherever I want because they really can only go in two places. And then from there, um, the locants of the actual methyl and bromine have to follow the assumed locants for the diene. I want my alkenes to both have their lowest locants. So in this case, that would be 1 and 3. So if I have one methyl, then my methyl must be coming off of there. And if I have 3 bromo, my bromine must be coming off of there. Um, I don't want to I don't want to jump over a lot in your notes, and I know that I'm already kind of being chaotic with these Zoom lectures. But I mentioned that cumulated diene where two alkenes meet at one carbon. But there are other types of dienes. One is an isolated diene. We call it isolated because the two carbons, or sorry, the carbons of the alkenes are separated from each other by sp3 hybridized carbons. Isolated dienes mean the carbons of the alkenes never come back and touch each other. I know this example makes it look like they just need to be separated by one carbon. They can be separated by a molecule. They're isolated from each other. And the other type is a conjugated diene, which means that instead of saying run, you say ran. No, I'm just kidding. But it does hit on that point again that conjugated doesn't really make sense to a lot of chemistry students. We throw this word around and people just think about conjugating verbs in Spanish. Thank you, Layla. A conjugated diene means they're related. Like conjugate acid and base are related to the original acid and the original base. They are the opposite of it. Conjugate verbs are related to each other. They are in just different tenses. Conjugated dienes are related to each other as an uninterrupted series of sp2 carbons. But I don't want to dance around the idea that it's about sp2 hybridized carbons. It has nothing to do with the sp2 orbitals, of which there are 3. It actually has everything to do with the p orbitals. And if those p orbitals, which constitute the double bond between those sets of carbons, if those p orbitals are all in phase, I know our Lewis structure makes it look like carbon 1 and 2 are bonded and carbon 3 and 4 are bonded with pi bonds. But why would I ever imagine that carbons 1 through 4 are bonded with a pi bond? If I can agree that carbon 1 and 2 can be bonded because their orbitals are overlapped and in phase, and carbons 3 and 4 can be bonded because their p orbitals are overlapped and in phase, and then it shouldn't be hard for me to say that those combinations might also be in phase, which leads to one extended pi bond. Our Lewis structure 2 times 2, 4 pi electrons. MO theory would suggest 2 of those electrons. It's not 2 electrons isolated between 1 and 2, 2 electrons isolated between 3 and 4. It's actually 2 of them conjugated across the entire span, and another 2 that behave more like isolated pi bonds, but are distributed across all four. God, electrons are so fun. Okay, three types of dienes. We will come back to diene reactions later in the semester. But I love MO theory. We just had a talk about MO theory, so it blends in. MO is the justification for why we call them conjugated, and it changes the reaction. Okay, let's remember what type of a reaction I would need in order to make an alkene. If I want to form an alkene, then, well, okay, truth be told, I could do an addition reaction. If I have an alkyne, I could consume one pi bond and I would be left with an alkene. That's true. One of the more common methods, and one thing that you will be doing on active, is to show how alkenes can be made by elimination reactions. Then I need to have two groups that can leave. And last week we called these A and B. I want to deviate from A and B for a minute, and I want to give you something um, more realistic. Almost always in the formation of an alkene, there's a hydrogen that's removed, especially in the reactions that you and I will learn next unit. One of them is a hydrogen. The other is a leaving group, which is a very original name, sometimes abbreviated LG. And these leaving groups can be halogens. Remember, halogens are what we'll use to represent, or X is what we'll use to represent halogens. They can be tosylates. You might remember from lecture last Wednesday that I wrote this up and somebody said, "What is tennessinium doing on the board?" Or maybe not actually naming the element, but TS is an element on the periodic table and it is not the element. It's a uh, tosylate group. It contains a sulfonyl and an aromatic ring. And we can also have protonated alcohols. I'm showing this as OH2 plus because if OH2, water, is bonded to the molecule, it will be protonated. And that is a good leaving group because by leaving and taking its electrons with it, it becomes neutral. So these are the leaving groups that we can use. I'm going to change the color of my of my OH2 plus because in getting these groups to leave, I have two different methods. If I'm using um, if I'm using a halogen or a tosylate, I'll use some sort of base, typically negatively charged, but it doesn't need to be. If I'm using water, I actually need an acid. Acidic conditions are needed to protonate the alcohol, turn it into a water, and help it behave as a leaving group. Either way, one group leaves and a hydrogen is removed from the adjacent carbon. If you guys remember, back in the mass spec unit, we said that carbons bonded to functional groups are often referred to as the alpha carbon. And these bonds cleave in mass spectrometry because there's often resonance with the functional group that stabilizes the cation that forms. So it's an interesting carbon. It's a carbon of interest. It's the alpha carbon, which means the carbon adjacent to it is the beta carbon. You know this if you know your alphabet. Alpha comes before beta. And so we refer to the hydrogen that leaves as a beta hydrogen. Okay, that means that I can look at my alkene and I can call this an alpha beta unsaturated group. The alkene is a pi bond between alpha and beta. So I would like you to look at the structures and I want you to consider, where is alpha? Is there more than one? Where is beta? Is there more than one? How many alpha beta combinations can I have? Are any of them the same, but just between different equivalent carbons? Are any of them different? Start by labeling alpha beta, identify that beta hydrogen, and then think about, what would that alkene look like if I made that group leave? And what would the alkene look like if I also took away one of the beta hydrogens? I'll start with the first one. Actually, all of these have only one alpha position. This alpha carbon is primary, which actually tells us how many beta positions there are. Alpha is only bonded to one position, so that's the only beta. There must be a hydrogen on that beta carbon because it's missing three bonds. So it's assumed, which means that I can elimination reaction. I can eliminate that leaving group, the halogen, and its beta hydrogen, and the alkene that I can make. Listen, if we called this molecule by its systematic name, we would call it eth, two carbons, ene, alkene. Yeah, but nobody a long time ago was really aware of what they were doing, so they call it ethylene because it's a two carbon alkene. Anyways, this is ethylene, CH2 double bonded to CH2. That's the only one. Up above, I have alpha, which is secondary. I have a primary beta to the left. I have a secondary beta to the right. A secondary alpha should have two different betas. You might suspect that this has two elimination products. A less substituted alkene to the left and a more substituted alkene to the right. And I know that alkene, we named that last week or last class. That's trans 2-butene. If it has a stereoisomer, then it's possible I could have the stereoisomer form as well. So there are actually three different alkenes that can form. Two of them are stereoisomers, cis-trans stereoisomers. Now, up above, um, I kind of want to move through these a little bit faster. Tertiary alpha means that I could have three different alkenes to the beta hydrogen on the left, beta hydrogen on the methyl group, tertiary beta hydrogen on the right. Then I see another secondary alpha. So I could have a more substituted beta hydrogen removed up above, a less substituted beta hydrogen removed to the right. Finally, I have a primary alpha. I want you to identify where the beta hydrogen is. See if you can describe it in the chat, if you're feeling brave enough. Man, my alphas, I apologize. My alphas are not coming across well on here. If you're working on drawing out some of the possible alkenes, take that central structure and look at the pi bond that can be made between each of the beta carbons with alpha. I've got three different products. I want you to be getting into a habit of identifying a group that can leave, a halogen, a tosylate. We'll look at alcohols in unit 5. And then take a hydrogen if you need to. Keep drawing out those hydrogens until you can identify it. Pull it out. Replace the two groups with a pi bond between the carbons. And if all you're doing is practicing that and not thinking about it, then you'll give me that this final product forms 2,2-dimethyl propene. The carbon bonded to the beta hydrogen is always bonded to the alpha carbon. Yeah, so to call it a beta hydrogen, beta to what? Hydrogen's only bonded to carbon. So a hydrogen doesn't have multiple groups, but a beta hydrogen is implied by being attached to a beta carbon. Let me give you some more examples, like a methyl hydrogen. A hydrogen can't be a methyl. So a methyl hydrogen is a CH3 a hydrogen on a CH3. We can also call that a primary hydrogen. Primary was used to describe carbons. We didn't use it to describe hydrogens. So we can say a primary hydrogen, a secondary hydrogen, a tertiary hydrogen. Kind of the way that we call things a primary alcohol, a secondary alkyl halide, a tertiary ether. It describes the carbon that it's bonded to. Great. I haven't seen anything in the chat yet about my 2,2-dimethyl propene. I hope nobody logs off right after drawing this. Anybody want to critically think about that structure? That came across so weird. I know you want to. Anybody want to display their critical thinking in the chat about that structure? It does matter. Too many bonds. Broke its octet. 2,2-dimethyl propene can't exist. So how am I supposed to form this alkene? How do I get my primary alpha carbon and my quaternary beta carbon to form an alkene that can't exist? It's not a bad idea to think that maybe a methyl group is the leaving group, or a methyl group leaves. Um, but we are looking at beta hydrogens leaving. How many beta hydrogens did our alpha carbon have? No beta hydrogens. So just because we have patterns for predicting alkenes doesn't mean everything is able to react to form an alkene. My screen is so messy, and one reason I don't like this is because if you're taking notes on the worksheet, then your worksheet probably looks as messy or worse than mine. Uh, I have to recommend going back through the data, or going back through the lecture, going back through the examples, and organizing it, crafting the narrative again. So this last one, I'll say yet. There are ways that you could get there. I'm not actually sure that we'll get back to this example, but there are some really creative ways that chemists can make these molecules rearrange their groups. So we're not going to look at what can form from this. We're going to say no beta hydrogen, no elimination. All right. I I realize that there was something I never put in my notes for on my worksheet for this unit, and I realize it like right now. So there's a tangent we need to go on. It's important. It is one of the learning objectives, and it is stability of alkenes. First, let's consider how the degrees of substitution impact the stability of an alkene. Ethylene is our base alkene. And we can functionalize it. For instance, we can have chloroethylene, dichloroethylene, tetrachloroethylene. But ethylene would be called non-substituted. The carbons of the alkene are only bonded to each other and hydrogens. Excuse me. When I remove one of those hydrogens and I replace it with a bond to a carbon, I get a mono-substituted alkene. If I remove two bonds, I get di-substituted, but the di-substituted family is bigger than you might expect. First, I could have a di-substituted alkene where it's one carbon, one new carbon group bonded to each carbon of the alkene. And the stereochemistry, because now both carbons are bonded to two unique groups, the stereochemistry is cis. Or I could have those two new carbon groups, one to each carbon, but the stereochemistry is trans. Or I can have two new groups, but they're both bonded to the same carbon of the alkene, which means that this is not a stereoisomer. This example isn't. I could put a chlorine where the CH2 is, and that would create stereoisomerism without changing the substitution because R here to impact substitution must be a carbon group. Now, I want you to think, I'm not finished, but I want you to think about what order am I listing these alkenes in? Is it random or from non-substituted to mono to di, and di being cis, trans, and then terminal? This is the language that I think works best in describing this group. This is a terminal di-substituted. The other two, you can see how the alkene is within a carbon chain, internal. But here the alkene stops at the edge of a carbon chain. So it's a terminal di-substituted. How do you think stability is changing? Are things becoming more stable in the list that I'm creating, or are things becoming less stable? And if you have an idea of which one, what gives it away? I would hope that these two give away the list that I'm making. The fact that I put the cis di-substituted above the trans di-substituted, we already know that the zig-zig Newman projection is an eclipsed Newman projection, which is high energy, and the zigzag is actually staggered, which is lower. So the cis alkene has steric strain that the trans alkene doesn't have. So a trans alkene must be more stable. A cis alkene is less stable. We're starting to see that stability increases with substitution. An alkene is less reactive, an alkene is more stable if it is more substituted. Wow, my stability came across brilliantly. Okay. Oh God. Um, stability, I'm just gonna say that again. Stability trends with substitution. Stability increases with increasing substitution. And the cis alkene and the trans alkene di-substituted have the same substitution. So we rank them by sterics. And I'll come back and I will justify using resonance why the terminal di-substituted alkene is more stable than the cis or trans internal alkene. But our last two degrees of substitution, I can have a tri-substituted alkene, and I can have a tetra substituted alkene. If you remember back to the beginning of Unit 4, we got into Section 6, and I gave you guys some terminology. I said that we would be following Zaitsev's rule, which says that elimination reactions, ones that form alkenes, prefer to form the most stable alkene, which means that they prefer to form the most substituted alkene. This is our most stable, least reactive, sits lowest in energy. And part of the question is why? Well, first, I want to remind you that these carbons share electrons in a sigma bond between them, and they share electrons in their pi bonds. But do you see how stretched out I have to make my pi bonds just to try and get the edges, or sorry, how stretched out I have to make my p orbitals just to get the edges to touch a little bit so that I have overlap. The electrons in the sigma bond are fairly concentrated. The electrons in the pi bond are fairly spread out, meaning the region where the electrons are is actually a little electron deficient. The electrons have to spread themselves out so far that it's almost like it's partial positive. So if I can get these other groups that are attached, and specifically if I can get bonds that they have and the electron density from those bonds, to overlap. That's actually the exact same thing that caused torsional strain in our Newman projections. These bonds would overlap with each other on adjacent carbons, and the electrons would push each other away, and our eclipsed conformation would try to fall into a lower energy state. It's like passing magnets against each other with the like end facing. They just repel as quick as they can. But it's the opposite. It's like torsional strain, electron repulsion, but it's called hyperconjugation. I ran out of space. And hyperconjugation, much like all forms of conjugation, is a stabilizing force. This is electron stabilization. Okay, so I've got this big area with my p orbitals that doesn't have a lot of electrons in it for how big of a space it is. So if I can borrow electron density from other groups, then I'm less likely for my electron for my molecular orbital to have new electrons added in, so it's less reactive. It's not resonance, but it's like resonance. Okay. Um, Coming back to this star that I made in red on resonance, I'm actually going to clear some stuff so that I can redraw this. Oh, nice. I put this on your worksheet. I totally knew that. So in the middle, you'll notice that I've got that terminal disubstituted alkene. And I've got two resonance forms that I want to fill in, one on the left and one on the right. To the left, let's assume that the electrons have been taken by the less substituted carbon. Oh, sorry, I just noticed. I used equilibrium arrows, and I did not mean to use equilibrium arrows. Equilibrium says A turns into B and B turns back into A. But this is resonance. This is like saying one way to think about it is like this. The other way to think about it is like this. It's the same thing. Now we've practiced bond making and bond breaking and using arrows to communicate what we want to, what change we want to see. So this says take electrons away from the tertiary carbon, positive charge, and leave them at the primary carbon, negative charge. The other thing that I could do here is to take the electrons and give them to the more substituted carbon. That puts a negative up above on the primary sorry, a negative on the tertiary carbon, primary on the positive. Now remember, we just mentioned that a big open space can pull electron density from its neighboring bonds, like how electron repulsion from neighboring bonds repels electron pairs. This overlap of orbitals filled with electrons into something empty with electrons actually helps to stabilize that empty orbital. The structure on the left has more hyperconjugation. I actually don't like that it's called hyperconjugation because conjugation is when p orbitals overlap, and conjugation is when pi electrons are actually moving. Hyper makes it seem like it's that on steroids. It's actually not conjugation. It should be called hypoconjugation. It's similar. There is some moral support, and that's what I like to refer to this as. That positive charge is looking for electrons. And if it doesn't have friends there to help shield it, it will take electrons from anything. So I say that hyperconjugation is a moral support. Its neighboring electron density is telling that positive charge, it's okay, you're fine, just relax, exist, don't be so reactive. And the more groups I have, and the bigger those groups are, and the more they have electrons, the more moral support my positive charge gets, the more stable my positive charge is. Up here, I have less hyperconjugation, which means less stable. How does it work with the negative charge? Well, the negative charge is like the Newman projection. It wants to repel nearby electrons. So actually, the less it has to repel, the better off it is. It's less likely to do anything drastic like rapidly share its electron pair because carbon doesn't love holding on to an electron pair. if the carbon has an electron pair and you want to stabilize it and make it not very reactive and make it easier to form, then you need to make sure that that electron pair isn't being repelled by a lot of other electron groups. And by being on a less substituted carbon, it's got less electrons around it. How many electrons? It's got electrons from a CH bond, a CH bond, and then the bond back to the original carbon that it used to be bonded to. So it doesn't have a lot of electron density, has less repulsion. That makes it more stable. What about in our other resonance form? That lone pair, if your instructor wanted you to do well, he'd remind you to draw in your lone pairs because you know what happens when we assume. I want you to see that lone pair. I want you to think about it. If you recognize it in your assumption, that's great, but it takes some time to recognize it. That lone pair is surrounded by three other bonds to carbon, and those carbons, two of them, have three other bonds to hydrogens themselves, and one of them has two other bonds to hydrogens. There is a ton of electron density. And this hydrogen is just trying to sit there. So this is more electron repulsion, more strain, less stable. Why do my charges have opposite properties? Why is it substituted? Why is it my negative charge is more stable on a less substituted? Well, okay, they are opposite charges after all, so opposite trends make sense. I wouldn't expect oh, sorry, they're not all particles actually, because positive charge here is just representing a lack of electron density. I wouldn't expect opposite charges to lead to similar properties. So here is a justification for why terminal is more stable than here that my terminal alkene, which of course has a major resonance form and then has a more significant minor resonance form. It has a fairly stable charge distribution resonance form. Can I do something similar with my internal disubstituted? What if my lone pair goes to the carbon on the left and leaves a hole of vacancy of electrons on the right? And what if my and leaves a vacancy of electrons on the left? Which of these resonance forms is more stable? We still, of course, have our major resonance contributor minimum formal charge. But here, secondary positive charge placement, secondary negative charge placement on both of them. Neither is significant. Both would be equally likely. Neither will actually give any sort of stabilizing factor, stabilizing force. So here's a trend that's on your learning objectives for this unit. We're going to lay it out a little bit more clearly. Carbocation stability. Excuse me. If you notice in your notes, if you're taking good notes, you might notice this looks a lot like what we just laid out for alkenes. The difference between alkenes and carbocations, this positively charged carbon, is not a lot. Alkenes are sp2 hybridized. Carbocations are sp2 hybridized. Alkenes have this kind of lack of electron density that they need moral support from, and carbocations do too. So with increasing degrees of substitution comes increasing stability. And I don't like that my less than sign is the same color. I want to make this pop. More moral support, more blocking of that positive charge. It's more stable and more likely to form. And that's going to be relevant to a lot of the reactions that we run. There's another factor, and that's resonance. What's better than just blocking a positive charge on a carbon, distributing a positive charge, making it that no one carbon holds the entire charge? So we have things like allylic. Those are positive charges adjacent to an alkene. Those are in resonance with the alkene, and the positive charge is on two carbons. Better way of saying that is both carbons have a half positive charge. And we have things like benzylic, which is when the positive charge is adjacent to a benzene, and the positive charge can move throughout the ring. Four resonance forms. That means four carbons with a plus 1/4 formal charge. And it scales with substitution within resonance. Um, Non-resonance stabilized goes primary to tertiary. But if there is any resonance, if there's an allylic carbocation, a benzylic carbocation, starts over. Primary allylic is more stable than tertiary non-resonance substituted. Doesn't matter the degree of substitution. on the allylic carbon, that resonance plays a, a much more significant contribution. I want you to consider, since alkenes had stability that increased with substitution, do you think alkenes have any increase in substitution? Sorry, have any increase in stability that trends with resonance? If carbocations and alkenes share this property of increasing stability with substitution, do alkenes have any sort of uh, trend of increasing stability with increasing resonance? The answer is yes. That same trend is seen when stabilizing, uh, when analyzing the stability of alkenes. But come join me in OCHEM 2. By the way, I don't think I've said this in class yet, but I've committed to the Tuesday, Wednesday, Thursday 10 a.m. sections this summer. So if you guys are interested in taking OCHEM 2 over the summer, I've not yet decided on my fall classes, but I'll be doing that in the next week or two. Come and join me in OCHEM 2, and we'll actually talk about why conjugating an alkene in a linear chain is different than having benzene, which looks like a conjugated triene, but is actually just uh, so chemically different because of the stability that comes from cyclic conjugation. Aromaticity is pretty cool. All right. Wow. A lot of theory, a lot of concepts. What the heck does it matter? It matters because this resonance form that we just predicted is more major than the other, helps us predict chemical reactivity, and the way that it reacts often leads to carbocations, and knowing the stability of carbocations helps us predict the product that will form, the intermediate that will form, and the product that will form. So, understanding that the resonance of 2-methylpropene prefers a negative charge on the less substituted carbon and a positive charge on the more substituted carbon means that we can put partial charge character across a pure bond. We typically say that bonds between the same element have no dipole. It's not necessarily true. We can predict how charge would form, which means we can predict how electrons will behave, even across a pure bond like the carbon-carbon double bond. Let's fill in this reaction coordinate diagram. How many reactive intermediate species do you see? Oh, sorry. Let's look at the pink reaction coordinate diagram. How many reactive intermediate species do you see? One. one hump in the middle. Something forms, and then it reacts to give us something else. In the blue reaction coordinate diagram, it's the same thing. So what we're saying here is let's take something like our alkene and let's do a reaction. This is one again, you'll see in section 7 homework on active. Um, but let's do a reaction that we're going to learn next week in depth as well, the HBr reaction, HX addition. HBr is hydrobromic acid. I'm actually going to sketch out the HBr bond because I'm going to show it breaking. If HBr is an acid, what is the alkene? The alkene is a base. Okay, the alkene's a base. That means the pi electrons will react. Why? Because the pi electrons are the most reactive electrons. The pi electrons are in the HOMO. Okay, so oh, I see. The pi electrons react. Which carbons use the pi electrons and which ones lose them? Our charges already help us predict that. Our partial charges says that primary carbon, it's more stable when it has the electrons. That partial positive says that tertiary carbon, it's more likely to lose the electrons. So we have an arrow from our pi bond, bonds to hydrogen, HBr breaks. Let's recognize that two things could happen. A more stable carbocation could form. My CH2 becomes a CH3. Why is that more stable? Hyperconjugation. It's possible that my partial charge doesn't work the way I expect it to, and that the more substituted carbon uses the electrons, which means that I form a primary carbocation and my tertiary carbon becomes a CH carbon. But this is less stable because it has basically no hyperconjugation. Both of these pathways can exist. If you were to think of this as a three-dimensional map, I want to go hiking in the Uintas when I get back. And I can either go up to the left where the ridge is shorter and easier to hike over, or I can go to the right where the ridge is taller and harder to get over. Where am I going to go? I'm going over the short ridge. Let's take a different analogy because we like to say that we have consciousness, and if I'm really dedicated, I can go over it. Okay, let's say that these are a game of pinball, not pinball, skee ball. And in my game of skee ball, I have I've got my ramp where my ball is going to roll, and then I've got my different categories, and here's a hole I can get into, and then more and more. If I only add enough energy to get to that first hole, guess what? I'm going into that hole. I've added enough energy, and that's the easiest place for my ball to now get into a lower energy state. If I really crank up the energy on my skee ball, then I can get it all the way up and over. But it's not always likely that that's going to happen because before it gets all the way up and over, it already had the chance to fall down in energy again. And oftentimes that happens. We can control these processes. We use temperature. Sometimes we actually have to cool things down to -78 degrees Celsius, give it just barely enough energy to move so that the only thing it can do is cross over that lowest energy barrier. And sometimes when we want to do this crazy thing, we have to put in insane temperature and pressure. But when it comes to carbocations, the more substituted carbocation forms. Look at where the H added. Did the H add to the carbon with more hydrogen, or did the H add to the carbon with less hydrogen? The H added to the carbon with more hydrogen. The H adds to the less substituted carbon. And that is Markovnikov's rule. He just didn't understand that. He recognized that the hydrogen consistently went to the carbon with more hydrogen and had not yet the structural understanding of molecules to understand that it was because the carbocation formed where it received the most moral support. The carbocation that was the most stable was the one that formed. And then, of course, we get into anti-Markovnikov's rule. Those are just reactions where the partial charges of the reagents involved flip and allow us to take advantage of charge stabilized placement or charge placement stabilization. We're not done, but I'm having fun. Hope you are. Guess what? Um, if this red and blue map that we're reaction map that we're seeing, if this were three-dimensional, I want you to try and imagine for a minute that um that especially never mind on the sides, especially here in the middle, that if this were really a three-dimensional mountain range. So I don't like that. Do you see what I'm do you see what I'm saying? That it's got these physical connections between these spaces. And I'm realizing I'm kind of having a hard time showing that middle spot because of if it is a mountain range, then I shouldn't be able to see back into there. So it's like going, you see what I'm getting at? What if you did form that primary carbocation? I didn't show this earlier. I'm sorry. The bromide is a byproduct, an intermediate in that step. Is it possible that I could get to this primary alkyl halide as opposed to the tertiary alkyl halide that I get when the tertiary carbocation forms? As it turns out, no, it's really not likely that I could ever make this. And that's because even if the primary carbocation forms, seems like it's not catching up again. Even if my primary carbocation forms. It would take less energy for it to shift over and become the tertiary carbocation. So we see this change happen in chemical reactions where a less substituted carbocation forms and then rearranges. A hydride shifts and leaves in its wake a positive charge in a different place, a positive charge where it's more stable. And that doesn't take a lot of energy. You can see it on this map. That energy would just be popping over, sliding down. I don't need to really make or break a bond. I just need my hydrogen to shift. And that's exactly what we call this. We call this a hydride shift. Hydrogen with electrons, hydride. IDE tells us negative charge. Hydride shifts over a new, more stable carbocation is left in the carbocation and showing where it moves. That's because this is like a hole in the line at the DMV. The hole doesn't move. People move into a hole and leave a new hole behind them. We will also look at methyl shifts. This is if something like a methyl group moves over and leaves in its wake also a more substituted, more stable carbocation. And these in general can occur with alkyl groups. And one of the most relevant examples, although for now I don't mention this a lot in my classes and I don't show it a lot. Alkyl shifts with carbocation rearrangements is significant with ring expansions. Carbon-carbon groups will move. Within a ring structure, expanding how many carbons are actually in the ring. If that stabilizes bond angle and minimizes ring strain, angle strain, then there's an energetic favorability for doing that ring expansion. Getting back to Kirsten's comment earlier about that elimination that I said couldn't form. Well, the carbocation I'm showing right here on the bottom left, that primary carbocation, if I can get that carbocation to form, and it's hard because it's a high energy carbocation, it's not very stable. If I can get that carbocation to form, I can shift over a methyl group. And now I have a tertiary carbocation. I have three positions where I have beta hydrogens that I can pull from. So certain molecules that can't do elimination might be able to rearrange, but I have to be able to form and stabilize that carbocation and then allow that carbocation to rearrange in a more stable way. For example, I have my tri-substituted cyclopentane. When I analyze my atoms like I did earlier, I have alpha, which is secondary. I have a beta on the right. I have a beta on the left. So earlier, this was a molecule that I gave you guys and said you could predict what alkenes might form. This gives me the possibilities 3,4-dimethyl cyclopentene, or oh, oh, I drew it wrong. Sorry, let me redraw the one that's on the right. Those were the same molecule. Or 1,5-dimethyl. And yes, that is the lowest locant set at the first point of difference, following the rule where I have to count through an alkene carbon. I can make, we would predict I could make 3,4-dimethyl cyclopentene or 1,5-dimethyl cyclopentene, but the structure that I've given you is 1,2-dimethyl cyclopentene. The two carbons don't even include the alpha carbon. Why? It must involve a rearrangement. Just above, I gave you an example of how an alkene maybe could form a not very stable carbocation, which then goes through a preferential energetic, an energetically preferential rearrangement to form a more stable carbocation before going on to give a final product. So that is a carbocation rearrangement in addition reactions. And down here, we're seeing a carbocation rearrangement in elimination reactions. Carbocations can form in a lot of different reactions. If a carbocation forms, it has the potential of rearranging, and it will rearrange if it gives you something more stable, if it gives the molecule something more stable. Okay. Um, let's do this. I've got 10 minutes left. If you got now, oh, the joys of conferences. Hanging out with hundreds of people I don't know and getting sick. I'm seeing no questions, which means you guys are just like getting it. I have heard most challenging parts of this course um, is mechanisms, and maybe that's for lack of training, lack of instruction, or lack of good instruction, lack of good examples, lack of practice is usually what I just practice. But The other is synthesis, knowing what reagents to use, what reagents perform a change that you see, and especially multi-step synthesis, where you have these blank spots. You have a starting material and a target, and you've got to make several changes. And you have to know reagents that can make a conversion that can be used with new reagents to make another conversion to get to the final product that you want. Um, so this is essentially the end of section 7, and section 8 blends in, which is alkene addition reactions. We're not going to look yet at reagents that are needed to get us to form alkenes, but we're going to say if I take an alkene, what can I turn it into? I think that what I did last semester was I covered all of the reactions, and then in like the last day, I did mechanisms. Um, and then I learned this semester with my OChem 2 class, I need to front load mechanisms, front load things that are more challenging. That's what we did with spectroscopy. We front loaded NMR, and then we put mass spec and IR, which historically students have told me are the easier concepts to give you more time to master NMR, more time to work with it. Whether you decide to use that time or not is not my, it's out of my control, but giving you more time to work on these skills. So what I want to do is introduce a few reactions and then show the mechanism for one of them. Uh, I am thinking of changing this, and that's why I brought my other laptop. I just didn't find time to. So, reaction number 1, and I'll start by filling this out again next week when we come back to this. Reaction number 1 is the HX addition mechanism. This can be HCl, HBr, HI, HF, if you're not aware, is one of the most deadly chemicals that you can work with. So we won't be showing any HX addition. Oh, that's great. Sorry, HF. Did I say HX? All right. So HX addition, the reagent that we'd see is either HCl, HBr, HI. If I have this starting material, 2-methyl, 1-propene, the product that I get is 2-halo, 2-methyl butane. I said propene, I meant butene. I get a butane chain. I have added a halogen to a carbon that used to have a hydrogen. That hydrogen is no longer there, but this is not removing that hydrogen. This is an addition reaction. I'm not losing anything. This reaction has a carbocation intermediate, and it must have a carbocation intermediate because my structure has rearranged. We'll also talk about the stereochemistry. This is a random addition mechanism. That means the two groups don't add relative to each other. Sometimes they add to the same face, sometimes it's random, or it's sin. Sometimes it's sin, sometimes it's anti. It's random overall. And we'll also talk about the regiochemistry. This follows Markovnikov's law, Markovnikov's rule. So those are the notes on HX addition. It has a carbocation intermediate. The stereochemistry is random. The regiochemistry is Markovnikov because there is a carbocation intermediate. So, I want to show a mechanism for HX addition. So I'll come down to the second page of my worksheet, or the third page of my worksheet. I've got two different examples. One similarly has a carbocation intermediate that rearranges. One does not. One thing I forgot to show here were my reagents. The first step in this mechanism, and I'm going to show my elementary steps forming the products, and then I'm going to re-show those products and show an elementary step. But you don't have to. You can show these fully sequentially if you want to. The first step in the HX addition mechanism is an acid base step. I already know based on substitution which carbon is more likely to act as the base. I already know based on substitution which carbon is more likely to take the carbocation. The carbon with more hydrogen got the hydrogen. That's because the carbon with more hydrogen is more negative. That's because the carbon with less hydrogen has more moral support. There is no carbocation rearrangement. So my step 1A down here doesn't apply. I'm not going to show anything because um, it doesn't play a role in this mechanism. But some HX addition mechanisms, it does apply. It plays a meaningful role. My second step, and for this, the last step, is a nucleophilic attack. Bromide is an electron pair donor. It shares electrons with carbon and it bonds to the carbocation. There's your first mechanism. I need you to know it for your unit test at the end of next week because you will be graded on showing a mechanism for one of these four reactions that you see: HX addition, H3O plus addition, Br2 addition, or sorry, X2 addition, and halo ether, halohydrin addition. We will talk more about these next week. You've got a template for how I want you to learn these mechanisms. Um, and once I think we'll start with these reactions and their mechanisms, because the rest of it is just reagents and recognizing change. And that's something that if you want to, you can get started on now. Watch my old lecture videos, go through the textbooks, go through any textbook, learn reagents, learn their changes. Um, these are the four mechanisms, the four reaction mechanisms that we'll learn. Thank you guys for your time. Thank you again for putting up with me being on Zoom and not getting your breaks, not getting your active learning. I look forward to seeing you all again in person on Monday. Have a great weekend. Take care.